Hey y'all, welcome back. So we are pushing through this very, very long explain, but we really wanted to drive home what osmoregulation means, water balance, and provide us with as many examples of osmoregulation as we possibly can. So we're going to conclude our explain two, and then we're just going to have a couple of elaborates, and then it's a performance task, and then it's your final performance task. Dun, dun, dun. But that's not a part of this lesson. So let's get through this lesson to get to those. Aim, how does our body osmoregulate during exercise? So our do now, which is a nice fine print for us. A student cut three identical slices from a potato. She determined the mass of each slice. She then placed them in labeled beakers and added a different solution to each beaker. After 30 minutes, she removed each potato slice from its solution, removed the excess liquids with a paper towel, and determined the mass of each slice. The change in mass was calculated and the results are shown in the data table. Okay. Now in beaker one, we saw that the potato slice was placed in distilled water and that the potato slice gained 4 grams after being placed in distilled water. And as stated before, distilled water is 100% pure water, right? There is no salt, no minerals, nothing that's diluted in there. Even our tap water is not distilled. We still have minerals and other electrolytes found in our tap water. All right, so in distilled water, we see that it gained 4 grams, okay? In 6% salt solution, we saw that it lost 4 grams. And in 16% salt solution, we saw that the potato slice lost 4.7 grams. Ouch. Right? So we literally saw that in distilled water, water had to have moved into the potato slice because it gained 4 grams. And that 4 grams has to be water because in distilled water, that's the only thing that's in there is water. So water was able to diffuse into the slice, right? The concentration of water is much higher outside in the distilled water beaker than it is inside of the potato slice. So water is going to naturally move from high to low, okay? And then in numbers 2 and 3, we see that in any amount of salt solution, water is actually moving out because the concentration of water is higher inside of the slice than it is inside of the beaker. So water is going to leave. And we saw that from 6% to 16%, we lost a significant amount of grams in our potato slice. So number 1 says, identify the process that is responsible for the change in mass of each of these 3 slices. And by now we should know that we're talking about the movement of water, which is osmosis. All right. Another example or another possible answer that you could actually put down that would still be correct is diffusion, right? Because osmosis just simply means the diffusion of water specifically, right? You can also put down passive transport. We've never really used this term, but passive transport is the same thing as diffusion. And osmosis is a type of passive transport. All right. And now number 2 says, explain why the potato slice in beaker 1 increased in mass. It gives you a lot of lines here, but this is one of those one and done, like very simple explanations. Water diffused into the potato slice. That's it. That's how it gains weight. Just like if we were to gain weight, it's literally because we're holding on to more water than we normally do, or maybe we're holding on to like more fat, or maybe we gain more muscle. That's the only way that we would get heavier is if we gained something that would make us heavier. In this case, it's water that the potato slice gained. Part A, the importance of water balance in cells. So osmoregulation is the control of water levels and mineral salts in the blood. Osmoregulation is important at all levels of organization in an organism, cellular, organ, system, and whole body levels, right? So bacteria, which are only one cell, they have to maintain osmoregularity just the same way that we do at a whole body system level. Water levels and mineral salts in the blood are controlled to protect animal cells by stopping too much water from entering or leaving them. We want it to be nice and balanced. We don't want too much or too little. The concentration of water and salts is the same inside and outside of the cells. If the body cells lose or gain too much water by osmosis, they do not function efficiently. So let's take a look here, which was also based on our osmosis lab that we did with the onion cells. All right. So what is this depicting to us? Well, if we look at the small caption, it says the osmoregulation of red blood cells in different solute concentrations, right? So in a hypertonic solution, which is the first one, it gives us that the red blood cell is losing water, right? Because in a hypertonic, right, there's a higher concentration of water inside of the red blood cell than outside, and water always moves from high to low, right? So I'm going to just use the letter H and L to represent high to low. So H equals high and L equals low concentration, right? So in this hypertonic solution, right, we have a higher concentration inside, and water always moves from high to low, which is why we see an arrow leaving the cell, because there's a lower concentration outside of water, right, which is going to cause the cell to shrink, right? And when you think hypertonic and these like small shriveled up cells, I want you to think salt water, right? Very, very shriveled up salt water. That's what's going to cause them to shrivel up, right? They look a little thirsty if you look at them, right? They're like, where's my water going? Okay. I'm actually going to pump over to hypotonic, and I'm going to come back to isotonic in a second. So hypotonic, I like to think of hypo. I see the word hypo, which is here, and I like to think hippo, right? A hippo is a very large animal, so I'm going to imagine that these cells are getting larger because they're absorbing more water, which means that the concentration of water inside of that red blood cell had to have been lower, and the concentration had to have been higher outside of the red blood cell because water always moves from high to low, right? And that's going to cause it to swell. Whenever you think of hypotonic, I want you to think of good old distilled water, right? 100% pure water is always going to have a higher concentration than pretty much anything else that's diluted inside of it. Okay, so water is always going to move from high to low. If we put our cells inside of distilled water, just like we saw with the onion cells, they're going to become larger and larger and larger and larger, and they can swell and they can burst. So neither one of these, hypertonic or hypotonic, are ideal for our red blood cells or for any of our body cells, really. However, isotonic is ideal, right? This is a huge happy face because the concentration of water both in and out of the cell is equal, right? So if water is moving in, the same amount of water is moving out. It's very refreshing, it's very hydrating, and that's why those red blood cells look very, very, very happy, okay? And if we had to put some emojis to the other ones, hypertonic would be really sad. Hypotonic would also be really sad. And isotonic would be really, really happy. Let's look at these micrographs, which are real screen captures. So micrographs of red blood cells in different solute concentrations. Again, hypertonic, right? We literally see that there's some irregularity in some of these cells, right? They're like small, different shapes, right? They don't look as happy. Isotonic, we see that these red blood cells are almost perfectly circular, which is exactly what we want. That nice, beautiful circular shape to our red blood cells, right? That tells us that they're just very happy. And then hypotonic, yeah, they're circular, all right, but it looks like they're literally inflating a lot larger. And if they keep absorbing water, water keeps moving into them, they will pop. So this is not ideal either. We want a nice circular, but we don't want it to be filled up like a water balloon to the point where it can pop. Okay? So these two depictions are just showing us visuals of what we've been discussing. All right? Now let's wrap up with three bullet points rather. If the concentration of water is the same inside and outside of the cells, also known as isotonic, then there is no net movement of water into or out of the cell. The cells remain in their normal state. Again, this is very happy for us. If the water concentration is too high outside of the cell, hypotonic, then water enters the cell by osmosis. If too much water enters, the cell will burst. This is not great. And then finally, if water concentration is too low outside compared to inside of the cells, hypertonic, water will continuously leave the cells by osmosis. This causes the cells to shrivel up or to shrink up. That's not great either. Wah, wah, wah. Okay. All right. Now, we have our own depiction that we have here for red blood cell, right? In a hypotonic solution, right? Where there's a higher amount of H2O and a lower amount of solute outside of the cell than inside of the cell. So what does that look like to us as starting, right? So in our starting red blood cell, we place it in a hypotonic solution. H2O levels inside of the cell are low. Salt concentrations are high, all right? So as a result of that, salt is going to leave the cell. However, water is going to enter the cell, right? Because in a hypotonic solution, there's a higher amount of water and a lower amount of solute, in this case, salt, right? So as a result of this, the cells swells with water until ... the cell bursts open, right? Due to overhydration. So we didn't just hydrate, but we overly hydrated. And as a result, if it's going to burst open, right, like a water balloon, H2O is going to leave, right? Because it was just so much H2O in there. And again, I just put here, think water balloon with too much water. Okay, and again, we are not happy with this. Let's move on to isotonic solution, right? Where the amount of water is equivalent, right? It's at equilibrium, both inside and outside, right? So H2O is going to enter. However, H2O is also going to leave. Salt or solutes, salt is going to enter, but salt is also going to leave, right? So H2O, stable amount, and salt inside is also stable. And an isotonic solution, all right? Equilibrium is maintained. We are very happy with this, which is why we literally see here that H2O is still stable and salt is still stable, right? This is ideal for our cells. In a hypertonic solution, we see that outside of the cell, there is a lower amount of H2O and a higher amount of solute, right? Well, H2O, sorry. H2O inside of the cell is going to be high. Salt inside of the cell is going to be low because the opposite is true outside of the cell. Inside, it's high. Outside, it's low for water. And then for salt, it's low inside and high outside, right? And these molecules are always moving from high to low. So just follow from high to low. That means that H2O is going to leave. Salt is going to enter, right? And then as a result, the cell shrinks until dehydration occurs inside of the cell, right? H2O is constantly leaving. Right? Causing them to become shriveled up, right? And again, this is really sad. We're going to draw a little teardrop. You don't want this. Even though they can't spare the tears, you probably wouldn't even produce tears if your cells were like this, because your body's trying to conserve all of that water. And again, think a deflated water balloon. All right. So guys, just study what these words possibly mean. This is all going to be a part of your final performance task. So make sure that if you have any questions, write them down so that way you can ask when we finally see each other again in person. You guys are absolutely amazing. And the next couple of lessons are just going to elaborate a little bit more on osmoregulation. You guys are absolutely amazing. I'll see you next time. Bye.